The universe's childhood photos show something impossible. Astronomers looking back over 13 billion years are finding galaxies that look far too grown up for their age, like toddlers with the strength of adults. This video will guide you through the profound mystery of why some early universe galaxies developed faster than expected. A discovery that is shaking the foundations of everything we know about cosmic evolution. You will gain a clear understanding of the revolutionary theories, from exotic dark matter to stellar supernova, that could explain this cosmic paradox. We will see how cutting-edge telescope data is forcing us to reconsider the fundamental laws that built our reality. What does it mean if the universe grew up in a hurry? And could this rewrite the entire story of everything? But to feel the full weight of this cosmic shock, we need a firm understanding of what scientists expected to see in the first place. Our entire modern view of cosmic history is built on a powerful framework known as the Lambda-CDM model. Think of it as the universe's most successful instruction manual. A detailed recipe that has explained everything from the faint afterglow of the Big Bang to the vast web of galaxies we see around us today. Lambda stands for dark energy, the mysterious force accelerating cosmic expansion. CDM stands for cold dark matter, the invisible cosmic scaffolding that gravity uses to build structures. This model tells a very specific story about how the cosmos grew up, and it is a story of patience. In the beginning, after the explosive birth of everything, the universe was a hot, dense soup of particles. As it expanded and cooled, a pivotal moment called recombination occurred about 380,000 years after the Big Bang. This is when protons and electrons combine to form neutral hydrogen atoms, finally allowing light to travel freely. We see that released light today as the cosmic microwave background, a baby picture of the infant universe. From that point, according to the model, growth was a slow, hierarchical process. Tiny ripples in the density of dark matter, seeded by quantum fluctuations in the first instant, began to pull in more matter through gravity. These small clumps merged to form larger clumps, in a cosmic game of consolidation that took eons. Only within these growing dark matter, halos could normal gas hydrogen and helium begin to pool, cool, and eventually collapse to ignite the first stars. This era, known as cosmic dawn, was predicted to be a time of fragile beginnings. The first galaxies were thought to be small, irregular, and inefficient, their light dimmed by the fog of neutral gas that still filled the cosmos. They were cosmic toddlers learning to walk. The model predicted a clear, gradual timeline. It would take billions of years of mergers, of generations of stars living and dying to forge heavier elements, which astronomers call metals, and to build up the majestic, well-ordered spiral and elliptical galaxies we see in the more recent universe. Massive, metal-rich, and structurally complex galaxies were the hallmark of cosmic maturity, the result of a long and careful upbringing. This established, step-by-step timeline is not just a theory. It has been backed by decades of observations closer to home in our cosmic neighborhood. It set a firm and reasonable baseline for what the early universe should look like. And that is precisely why the new images from the edge of time are so utterly perplexing. They are not showing us cosmic toddlers. They are showing us what looks like fully formed adults, standing in a nursery where only infants should be. The shockwave began with a single, breathtaking image. When the James Webb Space Telescope unveiled its first deep field view, it was not just a picture. It was a portal, a clear window into a universe only 500 million years old. For the first time, infrared eyes saw past the cosmic dust and stretched light, revealing the nursery of galaxies in stunning, impossible detail. And what they saw there defied every expectation. These were not the faint, blobby infants predicted by our cosmic models. They were galaxies of shocking maturity, some already taking on elegant disk shapes, others glowing with the light of billions of stars that had no business existing so soon. One of the earliest and most startling examples is a galaxy now known as GLSSZ 13. Analysis of its light suggests it formed when the universe was a mere 300 million years old, a cosmic newborn. Yet its stellar mass, the total weight of all its stars, was already enormous. Its star formation rate was frantic, producing new suns at a pace that should have taken billions of years to achieve. Astronomers like Dr. Jane Rigby, who helped lead the telescope's early science, described a collective moment of awe and disbelief. The data was so clear, so robust, that it could not be dismissed as an error or a cosmic fluke. The universe's childhood album, developed by Webb, was filled with portraits of prodigies. These galaxies were not just growing up fast. They were sprinting through their development, reaching milestones of mass and structure that, according to our best theories, should have been impossible. This was not a minor adjustment to the timeline. It was a direct, observational challenge to the foundational story of how everything builds, a challenge issued from the very edge of time itself. The true shock was not the discovery of one cosmic prodigy, but the realization that the nursery was crowded with them. As the James Webb Space Telescope continued its survey of the deep sky, a clear and unsettling pattern emerged. This was not a single, freakish anomaly to be explained away. It was a census result, a statistical truth written in starlight. Across multiple independent survey projects with names like CEERS and JADES, astronomers kept finding the same impossible thing. Dozens of these massive, mature galaxies, shining from an era when the cosmos was less than a billion years old. The number density, the sheer count of heavy galaxies per cubic volume of the early universe, was far, far higher than any simulation had ever predicted. Imagine explorers arriving at a distant, uncharted continent. Their old maps, based on the best theories of the time, showed a few scattered villages. Instead, they find a landscape dotted with bustling, fully developed cities. That is the scale of the discrepancy now facing cosmology. The model said the early universe should be a quiet, sparsely populated frontier. The telescopes show a cosmic boomtown. To understand why this is so definitive, we have to look at how astronomers build this census. It is a meticulous process of cosmic detective work. First, they use the telescope's powerful infrared instruments to capture incredibly faint light that has been traveling for over 13 billion years. The expansion of the universe stretches this light, shifting it toward the red end of the spectrum. By measuring this redshift very precisely, they can pin down exactly how long the light has been traveling, placing the galaxy at a specific moment in cosmic history. Next, they analyze the color and brightness of the galaxy. The mix of starlight tells them about the population of stars inside. Are they mostly young, hot, blue stars, or does the light show the signature of older, redder stars? By fitting models to this light, astronomers can estimate the total stellar mass, essentially weighing the galaxy. This is where the shock became undeniable. Project after project kept weighing these ancient galaxies and getting the same impossible result. They were simply too heavy too soon. The methods have been checked and rechecked. The data from different teams converges. This is not a measurement error or a trick of the light. It is a systematic, overwhelming fact. The early universe, according to our best maps, was supposed to be a place of small beginnings. But the new census reveals a landscape already rich with giants, forcing us to ask a far more profound question. If the standard recipe for the universe got this so spectacularly wrong, what crucial ingredient did we leave out of the cosmic cookbook? The most straightforward answer is also the most extreme. Perhaps these ancient galaxies did not break any rules of physics. They simply worked with a ferocious, unprecedented efficiency, turning cosmic gas into stars at a rate that would shame any modern galaxy. To understand this, we have to journey back to the raw ingredients of the early cosmos. The universe began with only hydrogen, helium, and a trace of lithium. There were no heavier elements, what astronomers call metals, which act like a kind of cosmic dust, helping gas clouds cool and fragment into stars. In this pristine environment, theory suggests the very first stars, known as population 3 stars, could have been true monsters. They might have formed with hundreds, even thousands of times the mass of our Sun. Picture the difference between a single, raging wildfire and a carefully tended campfire. The campfire burns steadily using seasoned wood. The wildfire, however, consumes everything in its path with explosive, uncontrollable speed. These primordial stellar giants would have been cosmic wildfires. Their lives were brilliant and brief, burning through their nuclear fuel in just a few million years before ending in spectacular supernova. This process would have flooded their surroundings with the first heavy elements and intense ultraviolet radiation, potentially triggering the rapid collapse of nearby gas clouds into the next generation of stars almost instantly. There are even more dramatic mechanisms proposed. Some models point to the possibility of direct collapse black holes, where enormous clouds of pristine gas collapse not into a cluster of stars, but directly into a supermassive black hole at the galaxy's heart. This violent birth would unleash incredible energy, shockwaves that could compress surrounding gas and ignite a frenzy of star formation all at once. In this scenario, a galaxy could essentially be born in a single, glorious burst, reaching maturity in a cosmic blink rather than a slow crawl. It is a compelling idea that the early universe was a place of wild, untamed physics where everything happened faster and brighter. But even this theory faces serious challenges. Such an intense burst of activity creates powerful stellar winds and supernova explosions. These forces act like a cosmic hurricane, blowing the very gas and dust, the fuel for future stars, clear out of the galaxy. It is the ultimate paradox. A fire that burns too hot and too fast can starve itself, leaving behind only embers. Could these early galaxies have sustained such incredible rates long enough to build the massive structures we see? Or would they have burned out as quickly as they ignited? The evidence from Webb shows galaxies that are not just massive, but also show signs of structure and, in some cases, a diversity of stellar ages, hinting at more than a single, fleeting burst. This suggests we might need to look beyond just supercharged star formation to something even more fundamental shaping the cosmic landscape from the very beginning. This leads us to a far more radical possibility, one that rewrites the recipe of reality itself. The answer may not lie in the stars we can see, but in the invisible dark matter that surrounds them. According to our best measurements, all the stars, planets, and glowing gas in the cosmos make up less than 5% of the universe's total mass. The rest is dark matter, a mysterious substance that does not emit, absorb, or reflect light, revealing itself only through its immense gravitational pull. It is the hidden skeleton upon which the visible universe is built. The Lambda-CDM model, our cosmic instruction manual, relies on a specific type called cold dark matter. The term cold here means its particles move sluggishly, allowing them to clump together easily under gravity, starting with tiny seeds and slowly, patiently gathering mass over billions of years. This slow growth sets the pace for everything else. But what if that foundational assumption is wrong? Cosmologists like Dr. Carlos Frenk have long explored alternative theories. What if, instead of being cold and inert, some dark matter was slightly warm, meaning its particles moved a bit faster in the early universe? Or even more intriguing, what if dark matter particles could interact with each other through some unknown force, not just gravity? These seemingly small tweaks to the physics would have monumental consequences for how quickly cosmic structures could arise. To visualize this, think of building a sandcastle. With perfectly dry, fine sand, your efforts are frustrating. You can pile it up, but it keeps sliding apart. This is like cold dark matter. It clumps, but the process is slow and requires careful, layered buildup. Now, imagine that sand is just slightly damp. Suddenly, it holds its shape. You can build taller towers, more complex structures, and do it all much faster. That hint of cohesion, that extra interaction, changes everything. If dark matter had even a small amount of this cohesive property, it could have begun forming dense halos much earlier in cosmic history. These ready-made gravitational wells would have been waiting, like pre-built foundations, for the normal hydrogen gas to fall into and ignite stars. The entire timeline of galaxy formation would be accelerated from the very first step. This is not just a minor adjustment. It is a fundamental shift in our understanding of the universe's construction crew. The evidence from the James Webb Space Telescope, showing massive galaxies too early, could be the first observational clue that dark matter is more complex, more dynamic than we ever imagined. It suggests the cosmic scaffolding was erected in a hurry, forcing the visible universe to keep pace. Yet, even this elegant idea faces its own cosmic hurdles. Alternative dark matter models must still explain everything else we observe, from the detailed patterns in the cosmic microwave background to the large-scale distribution of galaxies in the modern universe. Changing one piece of the puzzle risks throwing the entire picture into disarray. So we are left with two profound, competing narratives. One says the stars themselves burned with a ferocious, forgotten intensity. The other says the invisible foundations of reality were laid down with impossible speed. But what if the truth is not a choice between these two options, but a terrifying combination of both? There is a third force that could reshape this cosmic timeline, one that is both violent and creative. Galaxies do not always grow in isolation. They can collide, merging in a gravitational dance that forges something entirely new from the wreckage. Our own Milky Way bears the scars of past mergers, and is on a slow-motion collision course with the Andromeda Galaxy billions of years from now. The standard model always included this process, but it was scheduled for the cosmic Middle Ages, after smaller galaxies had time to form and drift together. What if, however, the opening act of the universe was not a serene nursery, but a chaotic and crowded demolition derby? Imagine the first protogalaxies, still glowing with the light of their first stars, not drifting in vast emptiness but packed relatively close together in a denser, younger cosmos. Their mutual gravitational pull would be stronger, their orbits tighter and more unstable. Collisions and mergers could begin not in billions of years, but in mere millions. A single major merger is a transformative event. It funnels huge reservoirs of gas toward the galactic center, triggering explosive bursts of star formation. It can rapidly double or triple a galaxy's stellar mass in a single, catastrophic, and creative event. If this process started earlier and happened more frequently, it could be the engine that builds cosmic giants in record time. To test this, cosmologists run immense computer simulations, virtual universes governed by the laws of physics. By tweaking the initial conditions starting with a slightly denser distribution of dark matter, or seeding the first galaxies with more massive central black holes that stir the pot, they can watch what happens. Some of these adjusted simulations now show a fascinating result. They produce a universe where the first major mergers happen startlingly early, creating a population of massive, structured galaxies that look eerily similar to what the James Webb Space Telescope is actually seeing. It is a compelling narrative of accelerated assembly, where the universe's construction crew worked in frantic, coordinated teams rather than slow, solitary effort. But does the real data support this picture of an early cosmic demolition derby? The telescope's keen eye is looking for the hallmarks of these violent unions. Astronomers search for telltale signs like distorted shapes, tidal tails of stars pulled out by gravitational forces, or pairs of bright galactic nuclei spiraling toward each other. Early results are intriguing but mixed. While some early galaxies show asymmetric, disturbed structures hinting at recent interactions, many others appear surprisingly calm and orderly, even at these incredible distances. This suggests mergers were certainly a part of the story, but they may not be the sole, dominant explanation for the galaxy growth spurt. It forces us to consider that all these potential explanations, supercharged stars, exotic dark matter, and rapid mergers, might not be mutually exclusive. Perhaps the truth of the early universe is a combination of all these factors. A perfect storm of conditions that allowed for a brief, glorious era of hyper-efficiency. A period where the rules of construction were simply different. If that is the case, then we are not just looking at strange galaxies. We are looking at a lost chapter of cosmic history, an era of frantic innovation that was shut down as the universe evolved. Understanding why it ended is just as important as understanding how it began. Perhaps the entire framework for how galaxies are built is backwards. For decades, the dominant story has been one of cosmic assembly, a bottom-up process where tiny seeds slowly gather mass through mergers, like countless villages growing and uniting to form a sprawling metropolis. But the impossible galaxies from the dawn of time force us to consider a completely inverted narrative. What if the first great structures formed top-down? Instead of many small things coming together, imagine a single vast thing collapsing all at once. Picture an enormous, rippling sheet of primordial gas stretching across thousands of light years. Under its own immense gravity, this entire structure could have begun to fragment and condense, not into many small clumps, but directly into the skeleton of a massive galactic disk. It would be like watching a giant, cosmic cloud suddenly crystallize into an entire city in one swift, breathtaking event, bypassing the slow, town-by-town construction phase entirely. This idea, known as monolithic collapse or top-down formation, is not new. It was one of the early theories proposed before the cold dark matter model became so successful. But it was largely set aside because the bottom-up story so elegantly explained the universe we see around us today. The shock from the early universe is now pulling this radical idea back into the light for a serious re-examination. Could it explain the mature shapes we are seeing? Some of the ancient galaxies captured by the James Webb Space Telescope do not look like the messy, irregular blobs expected from recent violent mergers. They show surprising symmetry and evidence of rotating disks, orderly structures that suggest a more direct and coherent birth. If a massive filament of gas collapsed in a relatively smooth, controlled manner, it could naturally create such a spinning disk from the very beginning, a ready-made galaxy emerging fully formed from the cosmic clouds. The evidence for this pathway might be hidden in the motions of the gas within these ancient systems. Astronomers are now using the telescope's spectroscopic tools to look for the signatures of these vast, inflowing rivers of pristine material. They are searching for the telltale signs of a giant structure feeding its collapse, a cosmic waterfall channeling fuel directly into the heart of a newborn galaxy. Finding such patterns would be a strong clue that top-down formation was not just a theoretical curiosity, but a real, accelerated pathway available in the unique conditions of the early cosmos. This leaves us with a universe of competing blueprints. We have the standard, patient model of bottom-up growth. We have the possibility of supercharged star formation in a pristine environment. We have the potential for exotic dark matter building foundations faster than expected. We have the chaos of early mergers. And now, we have this resurrected idea of swift, top-down collapse. The profound truth may be that in the frantic first billion years, all of these mechanisms were in play. Different galaxies may have taken different paths to maturity, with some forming from monolithic collapse, others from rapid mergers, all fueled by physics we are only beginning to grasp. The early universe was not a place with a single rulebook. It was a cosmic laboratory, running every possible experiment in structure formation at once. But what could possibly power such a rapid, top-down collapse in the first place? The answer might lie in the darkest hearts of these ancient galaxies. At the center of nearly every large galaxy we see today, including our own Milky Way, sits a supermassive black hole, a gravitational monster weighing millions or even billions of times the mass of our Sun. Where these behemoths come from is one of cosmology's great puzzles, but their very birth could be the missing accelerant for the entire galaxy. The theory is startling. If the seeds for these supermassive black holes formed almost instantly in the universe's first 100 million years, they would not be passive occupants. They would be active, violent architects. Imagine a massive cloud of pristine gas beginning to condense. Under the right conditions, instead of fragmenting into a cluster of stars, the entire cloud could collapse directly into a black hole seed of staggering proportions, perhaps tens of thousands of solar masses from the very start. This is not a star that dies and leaves a black hole. This is gas deciding to become a black hole in one single, dramatic step. This seed would be a gravitational anchor of unbelievable power. Its fierce pull would act like a cosmic vacuum, violently sucking in the surrounding gas at a phenomenal rate. As this gas spirals inward, it heats up to millions of degrees, blazing with light across the universe as a brilliant quasar. But more importantly, this process releases a torrent of energy. Intense radiation and powerful jets of particles erupt from the maelstrom, flooding the infant galaxy. This energetic feedback is a double-edged sword. It can blow gas away, shutting down star formation. But in the dense, pressurized environment of the early cosmos, it might also do the opposite. The shockwaves from this central engine could slam into surrounding gas clouds, compressing them and triggering a frantic, galaxy-wide burst of star formation all at once. It is like installing a roaring jet engine into the frame of a prototype car. The engine's sheer power and vibration don't just move the vehicle, they shake the entire assembly line, forcing every other part to be built faster and stronger around it. The black hole seed becomes the galaxy's furious, beating heart, setting a frantic pace for growth that the slow process of stellar mergers could never match. This is why astronomers with the James Webb Space Telescope are now hunting for the faint, telltale glow of these primordial quasars. Finding a supermassive black hole shining brightly inside one of these impossibly mature galaxies would be a smoking gun. Evidence of that central engine driving the accelerated timeline. Early data is already hinting at this connection, with some massive early galaxies showing signs of powerful, compact energy sources at their cores. If confirmed, it means we are not just looking at galaxies that grew up too fast. We are looking at galaxies that were, from their very first breath, built around a monster. The very first moments of the universe might hold the ultimate key to this mystery. To find it, we must look not at galaxies, but at the oldest light in existence, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, is our most precise map of the cosmos in its infancy. The patterns in this light, tiny variations in temperature, are the imprints of quantum seeds, the primordial fluctuations that would one day grow into every galaxy, star, and planet. Our standard models assume these seeds were distributed in a very specific, statistically smooth way. But what if that assumption is wrong? What if the infant universe was born a little lumpier than we thought? Those slightly denser patches of matter would have had a gravitational head start, collapsing into galaxies much faster than the average. It is a subtle tweak with colossal consequences, like discovering the blueprints for a city called for stronger foundation pillars from the very beginning. The mechanism that could create such a lumpier start is tied to the most exotic moment in cosmic history, the period of inflation. This is the idea that a fraction of a second after the Big Bang, the universe underwent a staggering, exponential expansion, smoothing it out and stretching quantum fluctuations into cosmic-scale ripples. Inflation is not a single theory, but a family of models describing the behavior of a hypothetical field that drove this expansion. Slight variations in how this inflationary field evolved, or how it transitioned to the normal hot Big Bang, could have produced a subtle boost in the number of those high-density seeds. The result would be a cosmos primed for rapid construction, with more sites ready for early galaxy formation than our standard recipes allow. This is where meticulous data confronts grand theory. The Planck satellite provided our most detailed map of the cosmic microwave background, and its measurements are incredibly precise. They generally support the idea of a universe that started with nearly, but not perfectly, smooth initial conditions. The question now is whether the data has just enough wiggle room. just enough statistical uncertainty at the very edges of its measurements to accommodate a slightly lumpier beginning that could explain the James Webb Galaxies. It is a razor's edge in cosmology, where the quest to understand early galaxies pushes us to re-examine the fundamental physics of the universe's first trillionth of a second. This is no longer just astronomy. It is a deep dive into the quantum origins of everything, suggesting that the answer to our galactic mystery was written into the fabric of reality before a single star had ever shone. The foundation of this entire mystery rests on one critical measurement. How can we be so sure these galaxies are truly from the cosmic dawn, and not just closer objects in disguise? The answer lies in the most fundamental tool of observational cosmology, a phenomenon called redshift. When we look at a distant galaxy, its light has been traveling across the expanding universe for billions of years. During that immense journey, the very fabric of space itself has stretched, and that stretching pulls the light waves along with it, lengthening them. Just as the sound of a passing siren drops to a lower pitch as it moves away, the light from a receding galaxy shifts toward the red end of the spectrum. The greater the redshift, denoted by the letter Z, the longer the light has traveled and the further back in time we are looking. A galaxy at a redshift of 10, for instance, is seen as it was when the universe was only about 500 million years old. But measuring this shift with absolute certainty is a monumental technical challenge. The most reliable method is spectroscopy. Astronomers use the James Webb Space Telescope's powerful instruments to break the faint, ancient starlight into a detailed rainbow, a spectrum. They then search for specific, telltale chemical fingerprints in that light, like the distinctive absorption line caused by hydrogen gas at a precise wavelength. If that fingerprint is found but shifted far into the infrared, it provides a precise, gold standard measurement of the galaxy's redshift, and thus its distance and age. It is the cosmic equivalent of finding a dated signature on an ancient document. Yet, for many of the faintest, most distant candidates, capturing enough light for a full spectrum is incredibly difficult. This is where a more common, but less certain, technique comes into play: photometric redshift. Here, astronomers essentially take very precise color pictures of the galaxy through multiple filters. They then compare its overall color to models predicting how a galaxy's light should be redshifted. Think of trying to judge the age and health of a very distant tree. Through a thick, obscuring fog, you cannot see the details of its bark or count its rings. All you have is its overall silhouette and the faint, blended color of its leaves. From that, you make your best estimate. Photometric estimates are powerful for surveying thousands of objects at once, but they carry more uncertainty and are vulnerable to cosmic illusions. The most prominent alternative explanation for these massive early galaxies is exactly that: an illusion caused by cosmic dust. Could these objects actually be much closer, but simply appear red and faint because they are shrouded in vast clouds of dust that block their blue light? This is a serious and valid point of scientific skepticism that teams must rigorously rule out. To do so, astronomers look for subtle clues in the data. A dusty, nearby galaxy will have a very different spectral shape than a truly ancient one. The teams working with Webb data run thousands of complex computer models, testing both the high redshift and the dusty low redshift scenarios against their observations. Time and again, for the most robust candidates, the models decisively favor the interpretation that these are indeed primordial giants. The evidence is not based on a single measurement, but on a convergence of data, a consistency check that leaves little room for doubt. This painstaking work of cosmic chronometry transforms an astonishing image into a solid, data-driven fact, the bedrock upon which the entire revolution in our understanding is being built. This frantic pace of growth could not last forever. Every action in the universe sparks a reaction, and for galaxies, this creates a powerful system of checks and balances. Think of a galaxy not as a simple factory, but as a complex, living ecosystem. When stars ignite, they do more than just shine. The most massive ones burn ferociously and die young, exploding as supernova. These blasts unleash torrents of energy and hurl out powerful stellar winds, a hurricane of particles racing outward. At the same time, a hungry supermassive black hole at the galaxy's core, feeding on gas, can blast the surrounding space with intense radiation and jets of material. All of this furious activity injects tremendous energy back into the galaxy's reservoir of cold gas, the very fuel for making new stars. This energy heats the gas, making it too energetic to collapse, or it can even blow the gas completely out of the galaxy. It is a cosmic feedback loop, a self-regulating thermostat designed to prevent a galaxy from burning through all its fuel too quickly. In the modern universe, this thermostat works remarkably well. A burst of star formation leads to powerful feedback, which shuts down that burst, allowing the galaxy to cool and settle before perhaps starting another cycle. It is why galaxies today generally form stars at a measured, sustainable pace. But what if, in the early universe, that thermostat was broken? Or more precisely, what if it was never even installed? This could be the secret behind the galaxy growth spurt. The first galaxies were built from pristine gas, free of the heavy elements, the metals, forged in later stellar generations. This purity changes everything. Metals are incredibly efficient at cooling gas. They act like a radiator, allowing hot clouds to shed energy, condense, and form stars. But in a metal-free environment, gas cannot cool as easily. This might sound like it would slow star formation, but it could have the opposite, paradoxical effect. Without efficient cooling, gas cannot fragment into many small, sun-like stars. Instead, it may collapse in monolithic, catastrophic waves, forming only those monstrous, short-lived stellar giants we discussed earlier. The feedback from these giants is different. Their supernovae are unimaginably powerful, but they might be so violent that they are less like a regulating thermostat, and more like a bomb that clears the room entirely. In some models, this could create a stop-start cycle of extreme intensity. But in other scenarios, the sheer density of the early cosmic gas might overwhelm even that violent feedback. Picture trying to blow out a candle in a gentle breeze. Now try to blow out a bonfire during a hurricane. The wind from your breath is meaningless against the larger, more powerful forces at play. In the dense, pressurized nurseries of the early cosmos, the incredible winds from stellar explosions might have been swallowed by the surrounding chaos, unable to effectively halt the relentless inflow of new gas from the cosmic web. The thermostat, in essence, was stuck on hot. Star formation could run unchecked, a wildfire spreading through an endless forest of fuel. This lack of efficient self-regulation might have granted early galaxies a brief, glorious window of hyper-efficiency, a period where they could convert gas into stars at rates we simply never see in the calmer, more metal-rich universe of today. It was a golden age of construction with fewer safety regulations, allowing cosmic giants to rise at a breathtaking speed. That missing population of faint, unseen galaxies presents a profound challenge. Our entire understanding of the cosmic dawn depends on what we can see. But what if the universe's own childhood is hiding in the shadows? To answer that, we must confront a pivotal transition known as the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was filled with a thick fog of neutral hydrogen gas. This fog absorbed the energetic ultraviolet light from the very first stars and galaxies, trapping their glow and keeping the universe in a kind of cosmic dark ages. But then, something changed. As more and more of these luminous sources switched on, their collective radiation began to tear the electrons away from the hydrogen atoms, ionizing the gas and clearing the fog in vast, growing bubbles. This was reionization, the moment the universe turned the lights on for good. It is a fundamental chapter in cosmic history, but for astronomers today, it creates a serious problem of perception. The James Webb Space Telescope peers back to this very era. Its infrared vision can see through some of the dust that obscures light, but it is still primarily looking at the light from stars and galaxies, light that had to escape that fading hydrogen fog. This means we might only be seeing the most luminous, most powerful objects, the ones that were strong enough to ionize their own local bubbles and punch their light through to us. Think of standing on a hill in a deep, rolling morning mist. You can see the bright lights of a distant city and a few scattered, powerful lighthouse beams cutting through the gloom. From your vantage point, the landscape seems dominated by these brilliant, isolated beacons. But what you cannot see are the countless smaller villages, the farmhouses, the quiet roads still shrouded in the fog. Your census of the territory is inherently biased. You are only counting the giants. This is the selection effect that could be warping our view of the early universe. The census from Webb reveals astonishingly mature galaxies, but they may be the cosmic lighthouses. A much larger population of smaller, fainter, and perhaps more typical infant galaxies could be completely invisible to us, their light still trapped or dimmed by the last patches of neutral hydrogen. If that is true, then the early universe might not have been a boomtown of giants after all. It could have been a more familiar place, with a few extraordinary cities surrounded by a vast countryside of smaller towns, a distribution that would fit much more comfortably with our standard models of slow, hierarchical growth. The question, then, is how do we lift this cosmic veil? The answer lies not in starlight, but in radio waves. Neutral hydrogen itself emits a faint, characteristic radio signal at a specific wavelength of 21 centimeters. By the time this ancient signal reaches us, the expansion of the universe has stretched it to meters in length. Detecting this faint whisper from the dawn of time is the holy grail for a new generation of observatories, most notably the upcoming square-kilometer array. This colossal radio telescope, being built across South Africa and Australia, will act as a sonar for the cosmos. Instead of looking for the light that escaped the fog, it will map the fog itself. It will listen for the 21-centimeter signal from the neutral hydrogen that filled the spaces between those early galaxies. By creating a three-dimensional map of this fading hydrogen, astronomers will indirectly see the voids, the bubbles ionized by the first luminous sources, regardless of how bright or faint those sources were. It will reveal the full landscape, the lighthouses and the hidden villages alike, by showing us the shadows they cast in the primordial mist. Finding that missing population of faint galaxies would recalibrate our entire cosmic census. It would tell us that the rules of physics might be intact, and that we have simply been missing most of the players in the early universe's story. But if the square-kilometer array looks and still finds the universe was dominated by vast, cleared bubbles with few small galaxies to fill them, the mystery of the cosmic prodigies will only deepen. The next great leap in this story will come not from looking at the light, but from listening to the silence it left behind. The silent, ancient stars right here in our own galactic neighborhood may hold the answer. To understand the frantic construction sites at the edge of time, astronomers are turning to a different kind of science, galactic archaeology. This is the art of reading the history of our cosmos not by looking outward into the deep past, but by looking inward, at the oldest surviving citizens of our own Milky Way and its nearby companion, the Andromeda Galaxy. These ancient stars are living fossils, each one a time capsule with a chemical story etched into its light. When a massive star explodes as a supernova, it forges heavy elements in its fiery heart and scatters them into the surrounding gas like cosmic fertilizer. The next generation of stars forms from this enriched material, inheriting a specific chemical signature. By carefully measuring the precise amounts of elements like iron, carbon, and oxygen in an ancient star, galactic archaeologists can determine which generation it belongs to, and what kind of stellar explosion seeded its birth cloud. It is like finding layers of pottery in an archaeological dig. The deepest, oldest layers contain simple, crude artifacts. Higher layers show increasing sophistication and complexity, telling a story of technological progress over time. Our galaxy is that dig site, and its oldest stars are the deepest, most primordial artifacts we can directly touch. What their chemical fingerprints reveal is startling. Many of the most ancient stars in the Milky Way's halo, the sparse spherical cloud of old stars surrounding our disk, show signs of being enriched by just a single, previous generation of massive stars. This suggests they formed very quickly after the first supernova lit up the cosmos. The chemistry points to a period of extremely rapid early enrichment, a frenzied burst of element creation that seems to echo the frantic pace we infer from the distant galaxies seen by Webb. This creates a powerful, direct link across time and space. We can now compare the detailed chemical makeup of a 13-billion-year-old star in our backyard with the blended light of a galaxy seen at a redshift of 10. Do they tell the same story? If the ancient relics locally show evidence of a swift, intense period of early star formation, it strengthens the case that what Webb is seeing in the early universe was not a rare fluke, but a common, perhaps universal, phase of galactic adolescence. It suggests our own Milky Way, now a stately spiral, may have had a wild, explosive youth that mirrors the distant Prodigies. The ultimate question galactic archaeology asks is profound. Did all galaxies, including our own, undergo a rapid, intense growth spurt in their first few 100 million years? A foundational burst of activity that set their entire future course? Or was the early universe a place of diverse pathways, where only some galaxies won the cosmic lottery and grew up overnight, while others, perhaps like our own ancestors, took a slower, more meandering path? By reading the memories of the oldest stars, we are searching for our own origin story in the light of the most distant dawn. These grand theories are not just ideas on paper. They are forged in fire inside the world's most powerful supercomputers. To test our understanding of cosmic evolution, scientists build entire digital universes from scratch, vast simulations with names like Illustris TNG and EAGLE. These are not simple animations. They are complex virtual laboratories where the laws of physics are written into code, governing the life of billions of particles representing dark matter, gas, and stars over billions of years of cosmic time. The goal is to press start and see if the virtual cosmos that emerges looks anything like the real one we observe. For decades, these simulations have been remarkably successful, reproducing the large-scale cosmic web and the general zoo of galaxy types we see around us. But now, they face their greatest challenge, the impossible galaxies from the dawn of time. When researchers run the standard models forward, the digital universe unfolds with the same patient, hierarchical growth we long expected. The massive, mature galaxies that the James Webb Space Telescope sees at a redshift of 10 simply do not appear in these virtual skies early enough. They are missing from the simulation's childhood album. This creates a fascinating puzzle. Can we tweak the code of these digital universes to produce what we see? Or does their failure point to a fundamental flaw in our physics? The process of building a simulation is a constant balancing act between realism and resources. You start with the initial conditions from the cosmic microwave background, a slightly lumpy universe. You add the known ingredients, gravity, dark matter, ordinary gas, and the basic rules for how gas cools and forms stars. But that alone creates galaxies that are far too massive and chaotic. The missing ingredient, as we have discussed, is feedback, the self-regulating energy from stars and black holes that prevents runaway star formation. Adding this physics is what makes simulations like Illustris realistic, but it comes at an immense computational cost. Every supernova explosion, every burst of radiation from a black hole, is a tiny, localized event that sends shockwaves through the surrounding gas. Modeling that properly requires tracking unimaginably complex interactions, a task that can bring even a supercomputer to its knees. It is like trying to simulate every gust of wind, every ripple of heat, and every eddy in the global weather system all at once, in real time. To make the problem manageable, scientists must use simplified recipes, educated guesses about how these energetic processes work on scales too small to model directly. The feedback in current simulations might be too strong, too weak, or simply too slow acting in the early universe, Computational astrophysicists are now in a race to build the next generation of these digital universes. They are experimenting with new feedback recipes, allowing for more rapid gas accretion or earlier black hole formation. Some teams are trying to simulate much smaller volumes of the cosmos with unprecedented detail, hoping to capture the unique, frenzied physics of the first galaxies. Others are attempting to run thousands of slightly different versions, a cosmic ensemble, to see if any combination of parameters can spawn a Webb-like galaxy at the right time. The results so far are tantalizing but inconclusive. Some adjusted simulations can now produce a few massive galaxies early on, but not in the numbers we observe. The digital universe remains too orderly, too slow. This tension is where real discovery happens. If, after Herculean computational effort, the simulations simply cannot replicate the early universe as seen by Webb, the conclusion becomes unavoidable. The problem is not with our coding shortcuts or our feedback recipes. The problem is with the textbook physics we have programmed in from the start. The failure of our most sophisticated digital twins would be the strongest evidence yet that we need to rewrite a fundamental chapter in the story of the cosmos, searching for new physics that operated only in that brief, furious dawn. The data points toward a cosmos that may have been in a hurry from the very beginning. This realization carries implications far beyond astrophysics, touching on the very story we tell about existence. For generations, the dominant narrative of cosmic evolution has been one of patient, gradual ascent. Life, we believed, was the product of a long, slow climb from simple particles to complex chemistry, a journey that required billions of years of stellar alchemy to forge the necessary elements and stable planetary environments. It was a comforting timeline, giving the universe ample room to experiment and evolve. But if massive, metal-enriched galaxies were already shining when the cosmos was only 500 million years old, that entire timeline compresses dramatically. The conditions for complexity, the heavy elements, the energy sources, the stable galactic neighborhoods could have arisen astonishingly early. This forces a profound philosophical question. Does the universe possess an inherent, accelerated drive toward complexity? Is the emergence of structure and order not a slow, reluctant process, but an almost eager, built-in tendency of reality itself? We are accustomed to thinking of life as a late arrival to a nearly empty cosmic stage. But what if the stage was set, the lights were on, and the potential for actors was present almost immediately after the curtain rose? This reshapes our sense of place. If life-bearing worlds could have formed around stars in those ancient galaxies over 12 billion years ago, then life in the universe is not necessarily a rare, recent phenomenon. It could be an ancient and perhaps more common thread woven into the cosmic fabric from a much earlier epoch. Our own solar system, at 4.5 billion years old, would be a relative newcomer in a universe that has been biologically mature for eons. This challenges the narrative of gradual evolution on a cosmic scale, suggesting instead a model more akin to punctuated equilibrium. Perhaps the universe experienced a brief, explosive era of hyper-efficient construction, a frenetic, foundational burst that established the framework for everything to come, followed by a long, slower period of refinement and steady burning. In this view, we are not the products of a slow, steady climb, but the distant heirs to a sudden, revolutionary event at the dawn of time. The galaxies we see with Webb are not oddities. They could be the evidence of that revolutionary moment, the cosmic equivalent of a Big Bang for biological potential. This invites a quieter, more humbling reflection. We look to the stars to understand our origins, but if the universe grew up in a hurry, our entire history, from the first microbe to the rise of civilization, might be just a single, late chapter in a story that began with a frantic and glorious opening act. The Standard Model's struggle to explain these early giants has forced a long overdue review of the alternatives. For decades, the Lambda-CDM framework has been so successful that rival ideas often lingered on the scientific fringe. But when the reigning champion stumbles, every other contender in the room suddenly looks more interesting. One of the most persistent challengers is known as modified Newtonian dynamics, or MOND. This theory proposes a radical solution to the dark matter problem by suggesting we do not need it at all. Instead, it argues that our understanding of gravity itself is incomplete, especially in the extremely weak gravitational fields found at the outskirts of galaxies. According to MOND, gravity behaves slightly differently when its pull becomes incredibly faint, providing the extra force we mistakenly attribute to dark matter. For some, the impossible early galaxies present a tantalizing question. Could a modified law of gravity have operated even more strongly in the sparse, expanding universe of the cosmic dawn, providing the extra oomph needed to gather matter into galaxies at breakneck speed? While MOND has had some success explaining certain features of modern galaxies, it faces monumental hurdles when applied to the universe as a whole. It struggles to account for the detailed patterns in the cosmic microwave background and the observed distribution of galaxy clusters without adding some form of extra matter anyway. The James Webb data, rather than rescuing MOND, may have inadvertently made its task harder, as the theory now must explain not just modern galaxy rotations, but an entirely new and unexpected chapter of rapid early formation. Another class of alternatives looks not at gravity, but at the very constants of nature. What if the strength of fundamental forces, like electromagnetism or the strong nuclear force, were slightly different in the early universe? A subtle change in these constants could have altered how quickly stars formed, how efficiently they burned their fuel, or how powerfully they exploded. It is a profound concept that the rulebook of physics itself might have been written in erasable ink, with the laws we measure today settling into their current values only after the first frantic era concluded. While intriguing, varying constants face intense scrutiny. The light from distant quasars absorbed by clouds over 12 billion years ago shows the fine structure constant, which governs electromagnetism, appears remarkably stable across cosmic time. The evidence so far suggests the laws of physics have been constant, a bedrock principle that makes the universe comprehensible. To abandon it would be a last resort. The current consensus among most cosmologists is to exhaust every possible solution within the Standard Model first, tweaking the behavior of dark matter or the feedback from stars, before leaping to entirely new physics. This is the scientific process at its most rigorous, yet history reminds us that the most transformative breakthroughs often come from following the data, no matter how uncomfortable the path. The extraordinary evidence piling up from the edge of time may one day force us to consider that our universe did not just operate differently in its youth, but that it truly was governed by a different, more dynamic set of rules, a lost physics of the dawn that we are only now beginning to glimpse. This intricate dance between the seen and unseen might hold the final key. For all our talk of dark matter halos and stellar fireworks, the true engine of a galaxy's growth is the delicate, often chaotic interplay between two cosmic partners, normal matter and its invisible counterpart. Normal matter, the protons and neutrons that make up stars, planets, and us, is what astronomers call baryonic matter. It is the luminous actor on the cosmic stage. Dark matter is the invisible stagehand, the hidden scaffolding that shapes the entire theater. In our Standard Model, their roles are clearly defined and sequential. First, the dark matter slowly coalesces into a vast, spherical halo through gravity alone. Only then does the baryonic gas, the hydrogen and helium, seep into this pre-built gravitational well. It must then cool down, shedding energy through radiation, before it can finally condense and fragment into the glittering lights of stars. It is a stately, two-step dance, with dark matter always leading. But the galaxies from the cosmic dawn suggest this partnership might have been far more intimate and dynamic, a frantic tango where the lead changed hands. What if, in the unique conditions of the early universe, the baryons did not just passively follow? What if they pushed back and, in doing so, accelerated the entire process? This shifts the focus to the detailed, messy physics of the gas itself. In the modern universe, gas is enriched with metals and dust, which makes it very efficient at cooling. It is like a hot engine with a sophisticated radiator, able to settle down quickly. But the first gas was pristine, pure hydrogen and helium. Without metals, it could not cool as easily. This might seem like it would slow things down, but it could have created a bottleneck that led to a dramatic collapse. Imagine trying to chill a pot of boiling water. If you have ice, you can cool it steadily. But if you have no ice, the water stays hot, building up pressure until it finally explodes into steam all at once. In a similar way, the inability of primordial gas to cool efficiently might have caused it to accumulate in vast, hot reservoirs within the dark matter halos. These reservoirs would grow unstable, collapsing not into many small stars, but in monolithic, catastrophic events that formed those first monstrous stars or even direct collapse black holes. Here, the baryonic physics of cooling, or the lack thereof, dictates the tempo. But there are other baryonic forces that could have taken the lead. Magnetic fields, though weak, might have been seeded by the earliest processes in the universe. As gas flows twisted and compressed, these fields could have been amplified, providing a skeleton that guided the collapse and prevented fragmentation, again funneling gas into rapid, centralized star formation. Even more potent is radiation pressure. The first stars were not just luminous, they were torrents of ultraviolet light. This intense radiation smashing into surrounding gas clouds does not just heat them, it physically pushes on them like wind against a sail. This radiation pressure can compress gas clouds from multiple sides, triggering what is called triggered star formation, where one brilliant beacon forces the birth of others around it in a rapid, cascading chain reaction. In this scenario, the baryons are not just following the dark matter's gravitational lead. They are using their own energy to set the rhythm, turning a slow waltz into a frenetic jig. The dance becomes a feedback loop of incredible power. Dark matter creates the initial gravitational well. Baryons fall in and ignite spectacularly. Their radiation and explosions then stir up the dark matter distribution itself, potentially pulling more material into the center, which attracts more gas, fueling more stars. The partners are now pushing and pulling each other, accelerating the dance beyond anything our calm, sequential models predicted. This view reframes the early universe not as a place where one component ruled, but as a collaborative, if chaotic, studio where every physical process was dialed to its maximum. The tempo of structure formation was not set by a single conductor, but emerged from the frantic improvisation of all the players, visible and invisible, in that first, glorious cosmic band. The ultimate test of our theories will come from the next wave of cosmic explorers. While the James Webb Space Telescope has revealed the shocking existence of these ancient prodigies, solving the mystery of how they formed demands a different kind of observation, one that combines vast cosmic surveys with exquisitely detailed close-ups. The coming decades will see a coordinated, multi-messenger assault on the problem, with new observatories designed to gather the precise evidence we currently lack. Leading this charge will be NASA's Nancy Grace Roman Space Telescope, scheduled for launch later this decade. Think of Roman not as a microscope, but as a wide-angle lens for the cosmos. Its primary mission is to conduct enormous surveys of the sky, with a field of view 100 times larger than the Hubble Space Telescopes. Where Webb painstakingly studies a few deep, narrow fields, Roman will rapidly scan vast stretches of the universe, conducting a true cosmic census. It will find not just the brightest, most shocking early galaxies, but thousands upon thousands of their fainter, more ordinary siblings. This will finally answer the critical question of selection bias. Are we only seeing the cosmic lighthouses, or was the early universe truly dominated by giants? Roman's statistical power will give us the population data needed to know for sure, revealing the true demographics of the cosmic dawn and putting hard numbers on just how anomalous this rapid growth really was. But finding these galaxies is only the first step. To understand their inner workings, We need to dissect their light with phenomenal precision, and that is the domain of a new generation of ground-based giants. The Extremely Large Telescope, or ELT, being built in the Chilean desert, will be the world's largest optical telescope when it sees first light. With a primary mirror stretching an astonishing 39 meters across, it will collect over 10 times more light than today's largest telescopes. This immense light-gathering power will allow it to do something Webb struggles with: obtain incredibly detailed spectra of these faint, ancient galaxies. Imagine Webb's data gives us a blurry photograph of a distant person. The ELT's spectra will be like a high-resolution medical scan, revealing the internal anatomy. It will measure the motions of gas within these galaxies, showing us if they are chaotic whirlpools from recent mergers or smoothly rotating disks born from monolithic collapse. It will detect the faint chemical signatures of the first supernova, telling us exactly how many generations of stars lived and died inside them. This detailed forensic analysis will let us distinguish between the competing theories of their formation, turning speculative models into data-driven conclusions. The final piece of this multi-messenger puzzle listens not for light, but for ripples in the fabric of spacetime itself. The Laser Interferometer Space Antenna, or LISA, is a future European Space Agency mission that will open the window of gravitational wave astronomy to the lowest frequencies. While ground-based detectors like LIGO listen for the chirps of stellar mass black holes merging, LISA will be sensitive to the deep, rumbling waves produced by the mergers of supermassive black holes, the monsters that may have lurked at the hearts of those first galaxies. If rapid early growth was driven by frantic mergers, then LISA could detect the gravitational thunder from those colossal collisions, events that happened over 12 billion years ago. It would provide a direct, dynamical record of the assembly history of the earliest galactic cores, a completely independent line of evidence from starlight. Together, Roman, the ELT, and LISA represent a new era of cosmic detective work. One telescope will conduct the broad census, another will perform the detailed autopsies, and a third will listen for the echoes of ancient violence. Their combined data will transform this mystery from a collection of stunning images into a solved equation, finally revealing whether the universe's childhood was a unique era of lost physics, or simply a more intense version of the story we thought we knew. A galaxy's destiny may be written not by what is inside it, but by where it was born. The cosmos is not a random scattering of islands in an empty sea. It is a vast, interconnected architecture, a cosmic web woven from threads of dark matter and traced with rivers of hydrogen gas. The grandest structures in this web are the filaments, immense bridges stretching for hundreds of millions of light years, where matter flows along invisible highways of gravity. The first, most massive galaxies likely did not appear just anywhere. They were almost certainly cosmic royalty, born at the crowded intersections of these filaments, in the most fertile nodes of the entire universe. Picture a sprawling, continent-spanning river system. Most of the land is dry, but at the confluence of the mightiest rivers, you find the most fertile deltas, the places where nutrients concentrate and life explodes in abundance. In the early universe, those rivers were filaments of dark matter, and the nutrients were pristine hydrogen gas. A galaxy seated at such a nexus would have had an unimaginable advantage. Instead of slowly gathering its material from a sparse local neighborhood, it would be fed by multiple, colossal streams of fuel pouring in from all directions. This is the cosmic equivalent of a startup company receiving infinite venture capital on day one. The galaxy could grow at a breakneck pace, feasting on a continuous banquet of gas, rapidly igniting stars and building mass in a way a more isolated protogalaxy simply could not. This environmental head start could be the decisive factor that allowed some galaxies to reach maturity hundreds of millions of years ahead of schedule. But how do we map these invisible highways in the ancient cosmos? Astronomers use a clever trick of light, turning the universe itself into a projector. When the brilliant light of a distant quasar travels toward us, it passes through the faint, diffuse gas that traces the cosmic web. The hydrogen in that gas absorbs very specific wavelengths of the quasar's light. By the time that light reaches our telescopes, its spectrum is etched with a dense, black forest of absorption lines, each one a fingerprint of a cloud of hydrogen at a specific distance. This forest is not random noise. It is a detailed map. By analyzing thousands of quasar spectra, scientists can reconstruct the three-dimensional distribution of this intergalactic gas, revealing the ghostly outlines of the filaments and voids. Another powerful tool looks for a specific glow, Lyman alpha emission, which is produced when hydrogen gas is excited by intense ultraviolet light from young stars. In the early universe, filaments illuminated by the first galaxies can sometimes be seen as faint, nebulous halos or extended blobs of this characteristic light, directly imaging the cosmic scaffolding itself. The critical test is now underway with data from the James Webb Space Telescope. Are those impossibly mature early galaxies found preferentially at the intersections of these mapped filaments? Early analyses suggest a compelling yes. Many of these cosmic prodigies do appear to reside in what were likely overdense environments, the bustling metropolitan hubs of the young cosmos, while fainter, smaller galaxies are found along the quieter suburban filaments. This environmental clue is powerful. It suggests that while the physics of star formation may have been wilder in the early universe, the rules of real estate were already in force. Location, location, location. The galaxies that grew up too fast were not just born with better internal engines. They were born in the cosmic equivalent of a resource-rich capital city, with all the advantages that provides, forcing us to see them not as inexplicable freaks, but as the predictable, if spectacular, offspring of the universe's most fertile neighborhoods. The chemical makeup of a galaxy is its permanent record, a ledger of every stellar life and death that occurred within it. To read that ledger, astronomers rely on a fundamental assumption about the universe's stellar factories. We call it the initial mass function, a seemingly dry term for a powerful idea. It describes the distribution of star sizes at birth. In our modern galactic neighborhood, for every truly massive star that forms, hundreds of smaller, sun-like stars are born alongside it. It is a cosmic rule of thumb that appears remarkably consistent wherever we look in the nearby universe. This balance dictates everything about a galaxy's evolution. Small stars burn for tens of billions of years, providing steady light and stability. Massive stars are the dramatic, short-lived agents of change. They blaze with furious intensity, forging heavy elements in their cores before exploding as supernova, seeding the cosmos with the metals that are the building blocks of planets and life. The initial mass function sets the tempo for this entire cycle. But what if this rule was not a constant? What if, in the frantic, pristine conditions of the early universe, the stellar factories operated differently, producing a far greater proportion of those massive, short-lived stars? This idea is known as a top-heavy initial mass function. Imagine a cosmic maternity ward where, instead of a few large newborns among many small ones, almost every crib held a giant. The consequences for a young galaxy would be transformative and immediate. With a top-heavy initial mass function, star formation becomes an exercise in extreme efficiency. A galaxy could convert its gas into stellar mass at a staggering rate, because it is forming stars that are inherently more massive. More importantly, these stellar giants would live their entire lives in just a few million years, a cosmic blink. Their swift, violent deaths as supernova would then flood the infant galaxy with newly forged metals almost instantly. In a single, furious generation, the galaxy could leap from a state of pristine purity to one of significant chemical enrichment. To our telescopes, this would make the galaxy appear mature far ahead of schedule, glowing with the light of heavy elements that, under our standard rules, should have taken billions of years to accumulate. The galaxy's starlight would carry the signature of a population that lived fast and died young. Detecting this signature is now a primary goal for the James Webb Space Telescope's most powerful mode, its spectroscopy. By breaking the ancient light of these galaxies into exquisitely detailed rainbows, scientists can search for the precise chemical fingerprints left behind by different types of stellar populations. A top-heavy initial mass function would leave a very distinct pattern in the elemental abundances. For instance, the ratio of oxygen to iron is a key clue. Massive stars produce and release oxygen efficiently in their supernova. Smaller stars over longer timescales contribute more iron. If Webb's spectra reveal an overabundance of oxygen relative to iron in an extremely early galaxy, it would be strong evidence that its first generation of stars was dominated by giants. Other elemental pairs tell similar stories. It is forensic astronomy at the edge of time, reading the chemical autopsy report of stellar populations that vanished over 13 billion years ago. This search goes to the heart of the mystery. Were these early prodigies built by a different kind of star, following a recipe lost to the later, calmer universe? If the evidence points to a top-heavy initial mass function, it means the foundational processes of star formation itself were once more intense, more dramatic, and far more productive. The universe did not just build galaxies faster in its youth. It built the stars inside them differently, forging its first giants with a haste we can scarcely comprehend. The shape of a galaxy tells a story of its past. For years, astronomers believed the first galaxies would be chaotic and formless, the inevitable result of constant, violent collisions in a crowded young cosmos. Their portraits, as seen by the Hubble Space Telescope, seem to confirm this, often showing little more than faint red smudges, the blurry signatures of distant, turbulent systems. But the James Webb Space Telescope has brought those portraits into shocking focus, and the story they tell is different. We are not just seeing massive galaxies too early. We are seeing galaxies with a sense of order, with shapes that whisper of stability emerging from the chaos far sooner than anyone dared to predict. This is the puzzle of early galactic morphology, and it is rewriting the narrative of cosmic structure from the ground up. The most compelling evidence comes from direct, side-by-side comparisons. Take one of the earliest known galaxies, a system observed when the universe was barely 500 million years old. In Hubble's visible light image, it is a single, indistinct blob, a hint of light that offers no clues to its inner architecture. But in Webb's penetrating infrared gaze, that same blob resolves into something astonishing. It reveals a bright central core, surrounded by the delicate, faint glow of a rotating disk. This is not a messy, merger-driven blob. This is a galaxy with recognizable structure, a cosmic frisbee spinning in the primordial dark. The presence of such disks is a profound clue. Disks, like the one in our own Milky Way, require a specific set of conditions to form and survive. They imply a relatively calm history, where gas can settle into an orderly, rotating plane rather than being constantly stirred up by catastrophic collisions. They speak of angular momentum, a property of spinning motion that must be preserved as the galaxy forms. How could such equilibrium be achieved in what we thought was a universe of relentless chaos? One possibility is that these galaxies were built not by a series of violent mergers, but by a rapid, smooth, and continuous rain of cold gas from the cosmic web. Imagine a galaxy forming at the quiet confluence of several dark matter filaments. Instead of other galaxies smashing into it, a gentle, sustained inflow of pristine hydrogen flows along these invisible rivers, feeding the growing disk. This gas would carry with it a shared sense of rotation, a coherent spin that allows it to settle naturally into a rotating structure as it cools. It is a top-down, monolithic form of growth that bypasses the messy middle stage of countless collisions, allowing a stable disk to emerge fully formed, almost from the very beginning. Another, equally radical idea is that the mergers themselves were different. Perhaps the first protogalaxies were so rich in gas that when they did collide, the event was less a destructive crash and more a smooth, gentle merger. The vast gas clouds would have simply flowed together, their angular momentum combining to create a new, stable disk almost seamlessly. This would be like two whirlpools in water, gently merging into one larger, calmer vortex, rather than two solid objects shattering on impact. The internal dynamics of these first systems must have been finely balanced. A dance between gravity pulling material inward and rotation flinging it outward, all while intense stellar feedback tried to blow the entire structure apart. That any disks survived at all suggests this balance was achieved with surprising speed and efficiency. The morphology we see is a frozen moment in that dynamic struggle, a testament to forces that allowed order to crystallize out of the maelstrom far earlier than our models ever allowed. These are not the toddler's scribbles we expected from the cosmic dawn. They are the first careful sketches of a universe already learning to draw in straight lines. The implications of this accelerated timeline reach far beyond galactic construction sites, touching the deepest human question of all. If massive, metal-rich galaxies could arise within the first few 100 million years, then so too could their planetary systems. The heavy elements forged in those frantic early supernovae would have been swiftly incorporated into swirling disks of gas and dust around newborn stars, the very cradles for rocky worlds. This compresses the entire cosmic schedule for creating habitats. The window for life to potentially emerge in the universe does not just open a crack, it swings wide open, billions of years earlier than we ever presumed. The chemistry for planets, for oceans, for the complex molecules of biology, could have been available when the cosmos was still in its wild youth. This forces a staggering possibility upon us. If life took hold on even a handful of those ancient worlds, then the first civilizations in the cosmos might not be our contemporaries or our descendants. They could be entities whose history stretches back for billions of years longer than our own, civilizations of almost unimaginable antiquity. We are not pondering life that might be a few million years ahead of us, but intelligences that could have been contemplating the stars since before our solar system even condensed from a primordial cloud. This realization casts the famous Fermi paradox in a new and even more intense light. The paradox asks a simple, haunting question. If the universe is so vast and so old and life is at all probable, then where is everybody? The silence from the cosmos is profound. But if our new understanding is correct, that silence stretches across an even more immense gulf of time. The Great Silence is not just a spatial emptiness, but a temporal one. Civilizations with a multi-billion-year head start would have had ample opportunity to spread, to build, to make their presence known in ways we should easily detect. Their absence is not just puzzling, it becomes deeply mysterious. It suggests that something, some universal filter, is far more effective at preventing technological civilizations from arising or persisting than we hoped. Perhaps the very violence that birthed those early galaxies also made them sterile, sterilized by intense radiation from hungry black holes or frequent supernova. Or perhaps the path from simple chemistry to a spacefaring culture is so littered with improbable steps that it is a miracle we are here at all. Alternatively, it might hint that advanced intelligence, when it does arise, inevitably turns inward, or transcends into forms we cannot perceive, or chooses a deliberate and universal silence. This cosmic mystery of rapid growth now connects directly to our own existential wonder. Are we a lonely, early experiment in a universe just waking up to its potential? Or are we a late arrival to a party that ended eons ago, listening to the echoes in an empty hall? The galaxies from the dawn of time do not answer this, but they reshape the entire framework of the question, reminding us that our search for companionship is also a search through the deep archives of cosmic history. These cosmic revelations ripple far beyond the equations of astrophysics. Every time humanity's map of the universe is redrawn, our place within it is redefined. The Copernican revolution moved us from the center of creation to a planet orbiting an ordinary star. Edwin Hubble's discovery of an expanding cosmos revealed we lived in a single galaxy among billions, in a universe with a beginning. Each shift was a profound cultural quake, shaking the foundations of philosophy, art, and our deepest myths. The possibility of a universe that grew up in a frantic hurry is the next chapter in this story of cosmic humility. It suggests that the stage for existence was not patiently prepared over eons, but assembled with startling speed, as if the cosmos were eager to begin the experiment of complexity. For artists and storytellers, this is not just data, it is a new palette. Imagine literature that explores civilizations born in that first fierce light, their histories spanning tens of billions of years. Visual art might try to capture the impossible contrast of delicate galactic disks forming within a cauldron of primordial violence. This discovery reframes time itself, making our entire human chronicle feel like a single, brief footnote in a story that accelerated from the very first page. Our fleeting existence gains a new, poignant context against a backdrop of such ancient, hurried beginnings. Science communicators like Dr. Michelle Thaler often speak of the challenge and beauty of sharing these concepts. The goal is not to drown people in technicalities, but to reignite a primal sense of wonder. We share this story not as a list of facts, but as the greatest detective story ever told, one where the clues are written in ancient light and the mystery questions the very laws of nature. It is about fostering a shared curiosity about where we come from, and by extension, where we might be going. This journey invites everyone to look up and feel a connection to a cosmos that is stranger, more dynamic, and more creatively fertile than we ever dreamed. It transforms the night sky from a static tapestry into a living, evolving narrative, one that we are only now learning how to read. So we are left with a constellation of possibilities, each shining with its own compelling logic. On one side of our cosmic balance sheet sits the theory of supercharged star formation, a universe where the first stellar furnaces burned with a forgotten ferocity. The evidence from ancient stellar fossils in our own galaxy whispers that this might be true, that the chemistry points to a frantic early period. Yet the scale of the galaxies we see seems to demand more than just brilliant stars. It asks for foundations built with impossible speed, which points our scales toward the other major contender, exotic dark matter. Perhaps the invisible skeleton of reality had properties we have not yet measured, allowing vast halos to condense almost instantly from the primordial soup. This idea elegantly accelerates the entire timeline from the very first step, but it must still explain every other piece of our cosmic puzzle without contradiction. Then there is the chaotic beauty of rapid mergers, the cosmic demolition derby that could have built giants through frantic collisions. We see hints of this in some distorted shapes, but many of these ancient galaxies appear surprisingly calm and structured, suggesting mergers were not the only story. And we must always account for the quiet voice of observational bias. Our telescopes may be showing us only the brilliant lighthouses, while a hidden sea of fainter, more ordinary galaxies remains cloaked in the fading fog of the early cosmos. The true answer likely does not reside in a single column of this ledger. Science, at its best, is not about choosing one elegant story and discarding the rest. It is about the messy, collaborative work of fitting the pieces together. The early universe was a place of extreme physics, of higher densities and purer ingredients. In that unique environment, all these mechanisms could have been operating at once, amplifying each other in a perfect storm of creation. Imagine a vast construction site where the scaffolding goes up overnight. The workers are giants of unimaginable strength, and multiple crews are collaborating and competing in a race to build the first skyscrapers. That might be the chaotic, glorious reality of the cosmic dawn. This is how scientific understanding truly evolves. A stunning anomaly like these impossibly mature galaxies does not immediately destroy our old models. It first stresses them to the breaking point. Researchers explore every conceivable adjustment within the known rules, tweaking feedback recipes in simulations, searching for those hidden populations of faint galaxies, and re-examining the chemistry of ancient stars. Only when those avenues are exhausted does the conversation turn with both excitement and trepidation, toward the possibility of new rules altogether. The greatest breakthroughs are born from this tension, from the refusal to ignore data that simply does not fit. Today's leading hypothesis, whether it involves self-interacting dark matter or top-heavy star formation, is a stepping stone. It is our best current map of a territory we are only beginning to explore. With the next generation of telescopes waiting in the wings, that map will be redrawn, refined, or perhaps even replaced entirely. This is not a flaw in the process. It is the process itself, a relentless and humbling journey toward a universe that continually reminds us how much we have yet to learn. Our journey through the baffling maturity of the early universe reveals a cosmos far more dynamic and inventive than we ever imagined. We have stood at the edge of time, peering through the lens of the James Webb Space Telescope at galaxies that should not exist, cosmic adults in a nursery of infants. We have followed the trail of clues, from the possibility of monstrous first stars burning with forgotten ferocity, to the radical idea that dark matter itself might have different, more interactive properties. We have weighed the evidence for frantic mergers and monolithic collapses, each theory a desperate and brilliant attempt to explain the impossible. This is not a story with a neat ending, because the greatest mysteries never are. Instead, it is a snapshot of science in its most vital state, a field being reshaped in real time by the stubborn, beautiful insistence of data. The gradual cosmic timeline we once held as gospel is now a question mark, and that uncertainty is not a failure of knowledge, but its very engine. It underscores a humbling and exhilarating truth. We are still beginners in understanding the grand narrative of existence. Every new answer from the cosmos seems to unlock 10 new questions, a reminder that the universe is far stranger, more creative, and more surprising than our best models can capture. Let this discovery be an invitation, not to frustration, but to a deeper kind of curiosity. Look up at the night sky with fresh eyes. Those pinpricks of light are not just distant suns, they are chapters in a story still being written, a story that began with a frantic, glorious burst we are only just beginning to decipher. Embrace the beautiful uncertainty of science, for it is in that space of not knowing that true wonder and discovery are born. If this exploration of cosmic origins captivated you, consider subscribing for more deep dives into the universe's greatest secrets. We would love to hear your own thoughts on this galactic puzzle in the comments below.